Hello, my dear students, and welcome back. Today, we're going to tackle a very, very important idea from your unit on the dual nature of radiation and matter, Einstein's photoelectric equation. I know it sounds complicated, but trust me, this concept is not only crucial for understanding modern physics, it's also a favorite in your exams. We're going to break it down so simply today that you'll be able to solve any question on it with full confidence. So to start, let me ask you a simple puzzle. We've all sat near a bright red room heater in the winter, right? You can feel that intense heat, but it never gives you a sunburn. And yet, even on a day when it's not so sunny, a little bit of invisible UV light can burn your skin. How is this possible? Why does it seem like the color of the light is more important than how bright it is? To solve this little sunburn secret and the much bigger puzzle of the photoelectric effect, we first have to understand why the old, trusted rule of physics, something called classical wave theory, just completely failed to give the right answer. You see, this is where the old physics got completely stuck. The classical wave theory said that light is just a continuous wave. So a brighter light should be a bigger, more powerful wave, right? It should be able to push electrons out with much more force. But when they did the experiments, the results were totally different. It wasn't the brightness that was the main factor, but the light's color, or to be more scientific, its frequency. You know, this complete failure of the old rules, it was a big, big problem in physics at the time. But it also opened the door for a truly revolutionary new idea from a young genius named Albert Einstein, an idea about what light really is. Einstein's idea was actually shockingly simple. He said, look, forget about light being a continuous wave for a minute. Just imagine that light travels in tiny, separate packets of energy. And he gave these little packets a name, photons. So don't think of it as a wave. Think of it more like a stream of tiny energy bullets. Okay, to make sure this photon idea is crystal clear in your head, let's use a very simple analogy. Just imagine you're trying to get into a very exclusive concert. Now, at this concert, there's a very strict rule at the door. Let's say the light's frequency is like a minimum height requirement. Only people who are tall enough can get in. And the brightness of the light, its intensity, is just the number of people who are trying to enter. So one very tall person, that's our high-frequency photon, can walk right in, no problem. But if a whole crowd of 50 short people, our low-frequency photons, show up, they will all be turned away. It doesn't matter how many of them there are. So, this is the most crucial point to remember. Frequency is the height requirement. Intensity is just how many people or photons show up. Each photon acts all by itself. To kick an electron out of a metal, one single photon must have enough energy. A million weak photons can't all gang up and combine their energy to do the job of one strong photon. And this simple, yet incredibly powerful idea of the photon is captured perfectly in one of the most famous equations in all of physics. This equation is like the master key that solves the entire photoelectric mystery once and for all. And here it is, Einstein's photoelectric equation. The maximum kinetic energy is equal to h nu minus w. It looks simple, nah? But trust me, this one single line brilliantly explains every single observation from the experiments that had scientists scratching their heads for years. Let's break it down term by term. Think of it like a simple money transaction. The h nu part, that's the total energy the photon delivers. It's like the money the photon gives to the electron. Then there's w, which we call the work function. This is like an exit toll, or a ticket price. It's the minimum energy the electron has to pay just to escape from the metal surface. So what's left over? Well, that's Ke max, the maximum kinetic energy the electron has to fly away with after it has paid the toll. Come on, let's do a tiny example to make this perfectly clear. Imagine a photon comes and hits an electron inside a piece of sodium. This photon gives the electron 2.48 electron volts of energy. Now, the exit toll for sodium, its work function, is 2.3 eV. So what happens next? It's simple subtraction. The electron pays the 2.3 eV toll to get out, and whatever is left over, that 0.18 eV, is the kinetic energy it uses to fly away. See? The equation perfectly predicts exactly how much energy the electron will have. It's that simple, really. Okay, now for a very, very important part for your exams. Listen carefully. This topic has a few, let's call them silent killers. These are common misunderstandings that can very easily cost you precious marks. Let's make sure you don't fall into these common traps. This is the number one mistake I see students making. They think that if you shine a brighter light, the electrons will fly out much faster, with more kinetic energy. I mean, it sounds logical, but it is completely wrong. So here's the correct fact, the one that will get you marks. A brighter light just means more photons are coming per second. So yes, more electrons will get knocked out, but the energy, and therefore the speed of each individual electron, depends only on the energy of this single photon that hit it. And that energy is decided only by the light's frequency, its color. Remember our concert analogy? Just because more people show up at the door, it doesn't make them any taller. And here's the second big trap. Students often think, okay, one red photon is weak, but what if I use a super bright red light and just wait for a long time? Surely the energy will add up and an electron will pop out eventually. Again, this sounds logical, but it's not how it works. The reality is, the photoelectric effect is an instantaneous one-to-one deal. It's one photon in, one electron out, in a single moment. If that one photon doesn't have enough energy to pay the exit toll, if its h nu is less than W, then it doesn't matter if a million more identical photons come after it. The electron is not going anywhere. This is a key rule to remember. So as we wrap this up, I want you to understand that this idea of the photon isn't just some small topic for one chapter. It's a key that unlocks a much bigger picture in all of modern physics. You see, understanding this properly, it connects everything. It shows you exactly where the old wave optics theory from your previous chapters went wrong. And looking ahead, this idea is absolutely essential for understanding atomic structure, how atoms absorb and emit light in these exact energy packets. In fact, what you've learned today is the very starting point for all of quantum mechanics. So for your final quick revision, let's go over the absolute key takeaways. Point number 1, light is made of energy packets called photons. Point 2, an electron gets ejected only if a single photon has more energy than the metal's work function. Point 3, the kinetic energy of that electron depends on the light's frequency, not its brightness. And point 4, the number of electrons that come out, the photocurrent, depends on the brightness, not the frequency. Got it? And that leaves us with a final, really amazing question to think about. We just proved that light, something everyone was sure was a wave, can behave just like a particle. So what if the reverse is also true? Could a particle, like an electron, ever start acting like a wave? We'll explore that very exciting idea next.